Hello class! Today what we are going to talk about is properties of special parallelograms. Now in the previous videos we saw properties of parallelograms in general. These are things that were true for every parallelogram, such as opposite sides were going to be parallel, both sets of opposite sides were congruent, the diagonals bisect each other. That's true for every parallelogram, doesn't matter. But there are some parallelograms that are special cases, and so they have extra properties, extra things that are special just about them. And those three parallelograms are the rhombus, the rectangle, and the square. Now, a rhombus is this shape here. This is not a diamond. I know a lot of people back in elementary school learned this was a diamond. It is not a diamond. There's no such thing as a diamond shape. All right. This is a rhombus. A rhombus is a parallelogram that has four congruent sides. So all four of them are congruent. Not just the opposite sides, but all four. All right? That makes it a rhombus. A rectangle parallelogram that has four congruent angles, four right angles. So it's not just the opposite angles that are congruent, it's all four angles are congruent. So it has four right angles. Okay? Because the consecutive angles still have to be supplementary. So they still have to add up to 180, and they're congruent, so they're right. 180 there. And then you have the square. The square is basically a rhombus and a rectangle at the same time. It has four congruent sides like the rhombus. It has four right angles like the rectangle. It is a square. So all the sides are congruent, all the angles are congruent. This is a regular quadrilateral. That's what this says. All right. It is a rhomboidal rectangle or a rectangular rhombus, whichever one you like. Either way, it's both rhombus and rectangle at the same time. So all the sides are the same, all the angles are 90 degrees. Now, there are three theorems that we're going to look at that are specific to these special figures, special parallelograms. The first is the rhombus diagonals theorem. What this says is if a parallelogram is a rhombus, then its diagonals are perpendicular. It is a rhombus if and only if it has perpendicular diagonals. So, with a rhombus, the diagonals will be perpendicular to each other, which makes sense. If you remember, we had the perpendicular bisector theorem, said that, well, the converse of the perpendicular, said that if a point was equidistant to the endpoints of a segment, then it would be on the perpendicular bisector of the segment. And since a rhombus, the sides are congruent to each other, that means point A is equidistant to D and B, and so this is going to be the perpendicular bisector. All right? So it's not just going to be perpendicular, be a bisector for a rhombus, it's also going to be perpendicular for a rhombus. Okay. Next, the rhombus opposite angles theorem. What this says is a parallelogram is a rhombus if and only if each diagonal bisects a pair of opposite angles. Okay, so the diagonal AC bisects angle DAB into two congruent angles. Okay, same thing with the other diagonal. It's going to bisect these two opposite angles. Okay, so for a rhombus and only for a rhombus, the diagonals not only are perpendicular to each other, but they are also going to bisect the angles. And this is only true for a rhombus. It's not true for any other parallelograms, only for a rhombus. Okay. Now, rectangle diagonals theorem. These are things that's true only for a rectangle, not true for rhombuses. And rectangle diagonals, what we have here is the diagonals are congruent to each other. Okay. So, with a rectangle, the diagonals are congruent. With a rhombus, the diagonals are perpendicular and they are angle bisectors. Okay? A rhombus does not have congruent diagonals. A rectangle does not have perpendicular diagonals. Okay? The diagonals of a rectangle do not bisect the angles. All right? That's only for a rhombus. Now what about squares? Well, squares, as we said, are both rectangles and rhombuses, which means for a square, these theorems that are good for rhombuses, this theorem that's good for a rectangle, all three of these are true for a square because a square is a rhombus and at the same time the square is a rectangle. All right? So, anything that's true for rhombuses is true for squares. Anything that's true for rectangles is true for squares. But just because it's true for squares does not mean it's true for rectangles or rhombuses. Okay? Squares are rhombuses. Rhombuses are not squares. All squares are rectangles, but not all rectangles are squares. All right? So, let's take a look at this. Let's see what we can do here. Open this up. What do we have? So, number one, for any rhombus MNOP, decide whether the statement that segment MO is congruent to segment NP is always or sometimes true. And then it wants us to draw a diagram and also explain our reasoning. Well, I'm going to start with a diagram because it makes it a little bit easier to figure out, is this always true, is this sometimes true? Okay, so first we're just going to draw generic rhombus. So remember, this is a parallelogram in which all of the sides are congruent. So there it is, parallelogram, need to mark it. All of the sides are congruent. So I know that it is a rhombus. I need a pen that writes a little bit better. We'll go with this one. And we need to label this, so we'll call this, well, that ain't much better, is it? M, N, O, P. Remember the points go around. All right. So we have our rhombus MNOP, and we need segment MO and segment NP. So let's draw segment MO and segment NP. And the question, are these two congruent to each other? And we can look at those and see, no, those aren't congruent to each other. MO is longer than PN, so that's no good. However, remember, there's a special case of rhombus, which is the square. So if it doesn't work for the general, you need to check to see if it works for the specific, see if it works for squares. So we have a square, MNOP. Squares, we've got right angles here. All sides are congruent. And let's see, what do we know about squares? You know, because I'm not the best artist, so those look pretty close, but let's see, do we have it there? That's better because my art's terrible. What do we got here? Well, squares are rhombuses, but we said it didn't work for rhombuses. But squares are also rectangles. And, oh yeah, rectangles have congruent diagonals, don't they? So, since a square is a rhombus, and since a square is a rectangle, this is going to be true for the square, but it's not true for the other just random rhombuses. So this is going to be sometimes true, sometimes, and we need to explain, well, because some rhombuses are squares. Not all of them, but some of them. So that's what we'll do. We'll say that some rhombuses, some rhombus are H-O-M-B. Actually, this would be I-I. This rhombii. That is the plural form of rhombus. It's not really called rhombuses. Most people will accept that, but it's actually rhombii. Some rhombii are squares. And it is true for squares, because squares are diagonals. Rectangles, and so the diagonals are congruent. All right, so there's number one. Let's take a look at number two. For any rectangle, okay, we're looking at rectangle, PQRS, decide whether the statement that angle PQS is congruent to angle RSQ. Is this always or sometimes true? You can draw a diagram, then explain your reasoning. All right, so we're going to start with the general, see if it's true for just random rectangle. And if it's true for, not true for random rectangle, then we'll check to see if it's true for the square. So we need just random rectangle, something that's clearly not a square. Rectangle, so all of the sides, all the angles are right angles, and this is PQRS. PQRS. And we are looking at angle PQS, so angle PQS. Okay, so we need a diagonal here. Okay, And the question is angle PQS, this one here, congruent to angle RSQ. So that would be this one right here. Are those congruent to each other? Well, let's see here. This is a rectangle, which means it is a parallelogram, right? So that means opposite sides are parallel, and I have these two angles. These are alternate interior angles, aren't they? So alternate interior angles are going to be congruent because we have two parallel lines cut by a transversal. So this doesn't matter if it's a square or not. This is going to be true for every rectangle. In fact, this would be true for any parallelogram at all. So this is going to be always true. Always true. Why? Because rectangles are parallelograms. Rectangles are parallelograms. Parallelograms. Which means segment PQ is always going to be parallel to segment SR, and so alternate interior angles theorem. Alternate interior angles theorem. Angles theorem. Theorem. So, alternate interior angles theorem. If two parallel lines are cut by a transversal, alternate interior angles are congruent. We learned that way back ages ago, back in chapter 3. Long time. All right, so there we go. Let's take a look at this next bunch. For numbers 3 through 5, we have the diagonals of rhombus ABCD intersect at point E. Given that the measure of angle BCA is 44 degrees, okay, that's marked for us. The length of AB is 9, all right, that's marked for us too. And the length of AE is 7, also marked for us, good. We need to find the indicated measure. So we need to find the length of segment BC. All right, so this segment BC, this is a rhombus, so we know it's a parallelogram, right? So it's congruent to its opposite sides, but we don't have the opposite side. But what is this? This is a rhombus. Remember the definition of rhombus? All four sides are congruent. It's an equilateral quadrilateral, right? All the sides are the same, and so that means if this is 9, this one is also 9 because all four of these are going to be congruent. All right. Okay, the length of segment AC, so that is this diagonal here, the whole thing. Well, it's a rhombus. Do we know anything special about the lengths of the diagonals of a rhombus? No, nothing special about the lengths, right? We know that they are right angles, we know they bisect angles, but we don't know about the perpendicular, rather. Okay, don't know about the lengths, except, if you remember, let's flip back over here. A rhombus is a parallelogram. And what do we know about the diagonals of every parallelogram? That's right, they bisect each other, which means AE is congruent to EC. So the length of AC would be 7 plus 7, which equals 14. So we'll put that equals 14. All right, and does this ask us to split? It does not ask us to split, so we don't have to write that down. Okay. Yeah, but that's because it's a parallelogram, and all parallelograms, the diagonals bisect each other. Okay, number 5, we need the measure of angle ADC. So that's this angle right here. Well, it's a parallelogram, so it's congruent to the opposite angle, which I don't know. It's also still parallelogram, so it's supplementary to the consecutive angle, which is this one, which I know part of. I don't know the whole thing. However, if you remember, over here we have the rhombus opposite angles theorem, which says that the diagonals of a rhombus bisect the angles. All right? Which means this diagonal AC is bisecting angle DCB. So these two angles are congruent to each other. So DCB measure of angle DCB is equal to 44 times 2, which is 88. And I know ADC is going to be supplementary to that because it is still a parallelogram. So I'm going to do 180 minus 88, and this is going to give me 92. So this is 92 degrees. All right. Because remember, all of those properties about parallelograms still work for rhombuses, the rhombi, and the rectangles, and also the squares. All right, so let's take a look at this one. Here we have the diagonals of a rectangle, EFGH, intersect at point I. Given that the measure of angle HFG is 31 degrees, that's marked for us. The length of segment EG is 17, and they did not write that down, so we just have to remember this is 17, the entire diagonal. All right, and they couldn't write it down because then it would look like there's this little piece with 17. It's the whole thing, entire diagonal. So first we need to find the measure of angle FHG. All right, so FHG, this angle right here, that's what we're looking for. A little bit more problematic, isn't it? It's congruent to the opposite angle, which we don't have. But what we can also do is we've got a triangle here, right? Triangle FHG. And we know that it's a rectangle, so this is a right angle. So we've got a right triangle. If I know one of the acute angles, I can find that other acute angle because the acute angles of a right triangle are complementary. So we can take 90 minus 31, and that's 9, and 8 minus 3 is 5. So this is going to equal 59 degrees. All right, next, HF. So that would be this diagonal. We need the length of the diagonal. We know the length of the other diagonal, EG, is 17. And if you remember, the diagonals of a rectangle are congruent to each other. So if EG equals 17, HF is also going to equal 17 because EG equals HF. Okay, so now we need the measure of angle EFH. So this angle right here. Well, again, this is a right angle, isn't it? Because it's a rectangle. So these are right angles. So I know part of it is 31. And I can just do 90 minus 31, which I already solved up there. This is 59 degrees. And also, not only that, as we said here, we have alternate interior angles are going to be congruent, right? So this angle is going to be congruent to that angle. Another way we can do it. All right, so now let's take a look at these last three. All right, so the diagonals of square LM and P intersect at point K. Given that the length of MK is 1/2, we need to find the other measures. So the only thing they gave us was the length of this one piece of the diagonal. Let's see. So first we need segment PK. Well, PK is the other piece of that diagonal, and this is still a parallelogram, right? So the diagonals are bisecting each other, which means this piece of the diagonal is congruent to that piece of the diagonal. So PK is also going to be 1/2. All right. Okay, now the measure of angle PKN. So PKN. Well, angles of the diagonal. What angle does intersect at? Well, if you remember, we have no theorems about squares, right? However, we do have theorems about rhombuses and rectangles. And which one says anything at all about the angles of the diagonals? It'll be right here. The rhombus diagonals theorem says that they are going to be perpendicular to each other. And since a square is both the rhombus and a rectangle, this is true because it's a rhombus. So that means this is going to be perpendicular, and so our angle is going to be 90 degrees because it's a rhombus. Okay, and last one, we need the measure of angle MNK. So we need the measure of this angle here. Well, it's a rectangle because it's a square, right? So since it's a square, it's a rectangle, that means that this whole thing is a right angle because it's a rectangle. But that still doesn't help us find this interior angle, this little piece of an angle, right? Except that it is also rhombus. And as we have the rhombus opposite angles theorem, says that the diagonals are going to bisect the angles. This is the only time when the diagonals bisect the angles is if it's a rhombus, and squares are rhombi. So that means not only is it right angle, it's also bisected, and we want that one right there. So since it's a right angle, the whole thing is 90 degrees. It's bisected, so we divide it in two, and we come up with the measure of angle M and K is 45 degrees. All right. So that's squares. So real quickly, just to review, we have three special parallelograms. The rhombus, which is equilateral, the rectangle, which is all right angles, it's equiangular, and the square, which is both a rhombus and a rectangle, has all right angles, and it has all four congruent sides. And we had these three theorems. So the diagonals of a rhombus are perpendicular, and they bisect the angles. Right? That's only for rhombuses, not for any other parallelograms, except for squares, because squares are rhombuses. And also rectangle diagonals theorem, which says that the diagonals of a rectangle are congruent to each other. Again, only true for rectangles, not true for rhombi, not true for other parallelograms, but also true for squares because squares are rectangles. All right? And that's that. I hope you found that useful, and I'll see you next time.